In this video, we're going to look at the confidence interval for the mean difference, which applies to paired data. And we'll look a little bit more deeply into why we used a paired design. So a confidence interval always has the same structure. It often starts with some sort of mean. Because we're looking at differences in a paired situation, this is the mean of the differences. And then we add and subtract the margin of error. The margin of error is constructed, it has the t-critical value, you need the degrees of freedom, and the significance level chopped in half. And you can find that by going to the t table or using the qt function in R, and then it's multiplied by the standard error. For paired data, it is just s over square root of n, and those are the standard deviation and sample size for the differences. And that's the formula. These confidence intervals, just like we saw in chapter 6.7, which was for the difference in means, that in itself is warrants a mention. This is the difference in means. And that's when we have independent samples back from chapter 6, chapter 7. Here, we are discussing the mean difference. So this is the mean of the differences versus the difference in means. Consider that. But regardless, we often can use this confidence interval as its own little hypothesis test. The question that we end up asking ourselves is, does the confidence interval contain 0? And if the answer is yes, then remember 0 is indicative of no difference. And that therefore would correspond to a hypothesis test in which we do not reject the null hypothesis. Right? 0, no difference. A non-rejection, not evidence for a difference. If the confidence interval does not contain 0, then that would support a conclusion of a rejection of the null hypothesis. Let's look at an example of calculating a confidence interval for the mean difference when we have paired data. I want to look at the example from the previous video in which we had the peak expiratory flow rate and we did a full t-test for it. So what I've done here is I've taken a couple screenshots of the example. We've got the data here and our conclusions. Let's go ahead and compute the confidence interval. And before we do that, I just want to mention that our conclusion was a rejection of the null hypothesis because of that small p-value. So I can anticipate, because there was a difference, now this was directional, so even more specific, there was a boost in the mean peak expiratory flow rate. But because there was some difference, when we calculate this confidence interval, I'm anticipating, so maybe I'm going to write this down, I am anticipating that the confidence interval will not have 0. CI, no 0. I'm going to take a brief moment just to write down all the elements that we need here.
We need the mean of the differences. We need the standard deviation of those differences. And we also need the sample size. The number of pairs, there were 9 pairs.
And to be completely consistent with the previous example in the previous video, we're going to use alpha 0.01. I know that's written right above here, but just to be completely clear here. To be consistent, what we're going to do is create a 99% confidence interval for the mean difference. That's what we're going to do. As always with these confidence intervals, we usually have most of the info that we need. I'm going to scroll up to the formula here. We've got the mean of the differences from the sample. We have the standard deviation. We have the number of pairs of those differences. What we usually need to do is figure out this t critical value. So I'm going to use R to do it, and I'll also use the t-table to do it. So we need to figure out the degrees of freedom and alpha over 2. So for t critical, we need the degrees of freedom and alpha over 2, but we know that the degrees of freedom was 8, yeah? Because it was 9 minus 1, which is an 8. We know what alpha is, the significance level, so half of alpha is half of 0.01, which is 0.005. I'm going to use this info to go find this in our t-table. Okay, I've opened up the t-table, 8 degrees of freedom, and I want to go to the column that says 0.005. So our t-critical value is 3.355. 3.355. Now, if I wanted to use R to do this, it would be using the QT function. In R, with the QT function, I'm not just going to type 0.005 because that would get me the critical value on the left side of the distribution. I want it on the right side. It really doesn't quite matter because we end up doing plus or minus anyway, but to be consistent with what we've done over here, I'm going to do 1 minus 0.005, comma, degrees of freedom, and that matches with what we have over here up to a third decimal rounding. Okay, let's get on with our calculation now that we have all the bits and pieces sitting in front of us. So it starts with the sample mean, which was negative 56.111111111 plus or minus the t critical 3.355. When I type that into R, I might be a little more precise. Our standard deviation 34.17398296 over the square root of our sample size, which is 9. Square root of 9. I probably could have just written that out. Okay, I'm going to take a moment here to perform the margin of error computation in R. Okay, I am typing this into R. Instead of square root of 9, I'll type a 3. And here is our margin of error, about a 38.2. Now I will do the operation to compute the lower bound and do the upper bound. So I've got a negative 94.3 up to about negative 17.9. And I believe because this was peak expiratory flow rate, this was given in liters per minute. So that is our confidence interval for the mean difference. And as expected, right, we have a negative 94-ish to a negative 17. As expected, this confidence interval does not include 0. So since 0 is not in the interval, that is as expected because in our previous video, we rejected a null hypothesis. So that's pretty cool. What I want to consider in the next half of this video is what if we had not considered the paired design and used a 2-sample t-test, the regular t-test, incorrectly, right? So when we crunch these numbers, and especially when we put this data into R, R doesn't know what the study design is. It is up to us as humans to know which test to use under which scenarios, so that way our conclusions can be valid. So let's run through a two-sample t-test where we would look at the difference in sample means as if they were independent from each other, and the standard error is s squared over n for each of the two samples, again as if they were independent, and it's those quantities summed under the square root. So if I scroll back up, I actually have all those numbers up here in this table. I've crossed them out from the previous video because you don't use those in the paired design. So down here I've got the mean of the before and the afters and their respective standard deviation. So I'm going to consider the befores as group 1 and the afters as group 2. So I've transcribed all those sample statistics into our formula here. In the interest of time, I'm just going to write out that this is about a negative 2.158. And our next step would be to determine the p-value for this, right? Remember, this was a left-tailed alternative hypothesis. So I would want the area to the left of this test statistic. And actually this is supposed to be negative 2 there. I still need R to perform that computation. And because this is a two-sample t-test, we need that degrees of freedom from that intense Welch-Satterthwaite method. And so that was degrees of freedom 15. So now I'm going to use R to calculate this p-value. I'm going to use the pt function, negative 2.158, comma 15. I do not need to double it because this was a one-sided directional alternative hypothesis. And we get 0.0237. Now we are ready to state our conclusion by using that p-value. And remember, the alpha was 0.01. Let's compare alpha with the p-value. The p-value in this case, 0.02 or so, is greater than alpha. So we would actually not reject the null hypothesis in this instance. But remember, what we're doing here is an incorrect application of the two-sample t-test. And let's consider now what happened with the paired test, which was the correct test to use. So as we just said, the regular two-sample t-test failed to reject the null hypothesis. But when we did the paired test, we ended up with a very small p-value and ended up rejecting the null hypothesis, and then we also demonstrated that with this confidence interval. The paired t-test, we did reject the null hypothesis. The big picture of hypothesis testing, remember that we don't ever really know what the correct conclusion is, because we're basing these conclusions on sample data, and we are inferring to populations based on sample data. So there's always a chance of making an error. Now, if you had to place a bet, which conclusion would you bet on? Well, since the two-sample t-test was not supposed to be used here, because we had paired data, so we violated the two-sample t-test requirement there. So its conditions for use were not met. If I had to place a bet, I would not place it on the conclusion from the two-sample t-test. So it likely resulted in an error. Now we don't know that, It's possible the paired t-test was erroneous, but we don't know. But if you had to place a bet, I would place it on the conclusion from the paired test. What is the type of error that this two-sample t-test probably made? Is it a type 1 or a type 2? Because this two-sample t-test concluded that we do not reject the null hypothesis, it could have been a type 2 error. So why are these tests coming up with different conclusions? It's because they focus on different aspects of the data. The paired test focuses on the variability between the before and after values. Those are the differences, yeah? Because we want to see if there was a change. Whereas the two-sample t-test focuses on the variability among the subjects. It does so by looking at their standard deviations, right? Standard deviation from the first and second sample show you how the values varied from subject to subject. Whereas in the paired t-test, and we look at the variability in the differences, which is why we have the standard deviation of the differences, SD. So we got a little deep here into why we use a paired t-test when we have paired data and how it focuses on different aspects of the data. In the next video, we're going to see what happens when we do not meet the paired t-test requirement. So that will be the focus of the next video, when we do not meet the normality requirement to do a t-test, but when we have paired data. See you there.